Welcome back. This is Professor Ridge and today's lesson 3.5, Transformations of Functions. And our first learning objective will be graph functions using vertical and horizontal shifts. Vertical shift. Given a function f of x, a new function g of x equals f of x plus k, where k is a constant, is a vertical shift of the function f of x. All the output values change by k units. If k is positive, the graph will shift up, and if k is negative, the graph will shift down. All right, so this is the most basic transformation, is the shift. It doesn't change the graph at all. So here's one of our toolkit functions that we should know how to graph real well. F of x equal to x squared, which makes this parabola. And if you were to go to, like here, this would be 1, 1. If we made our table of values, 0 squared 0, 1, 1, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, it didn't make, well, I can move this down. 3 squared is 9. Okay, and then you got the mirror image ones over here. Okay, now if I wanted to shift this graph up so many units, so the red one's my original. Now if I wanted to shift it up 1 units, I'm going to do x squared plus 1, or f of x plus 1. So if I do plus 1, you can see it shifts up. If I go to 2, you can see it goes up 2. Okay, so basically if I go negative 2.46, you can see it's the exact same shape, but just you're going to take the parabola and shift it down 2.46 units, right? So if it's positive, it goes up, negative goes down. So you see I got it going from negative 5 to 5. So it's just, the graph is not changing shape at all. It's the same parabola, just shifting it up or shifting it down depending on if k is positive or negative. And you do it by exactly k units. Example 1. Adding a constant to a function. To regulate temperature in a green building, airflow vents near the roof open and close throughout the day. Figure 3, so shown below, shows the area of open vents V in square feet throughout the day in hours after midnight T. During the summer, the facilities manager decides to try better regulate temperature by increasing the amount of open vents by 20 square feet throughout the day and night. Sketch a graph of this new function. So basically, they're just asking us to take this graph and shift it up by 20. So if we call this graph, let's see, what is this graph? Well, it's V as a function of t, right? So the output value is V, input value is t. So this is our y is equal to V of t. Now our new function is going to be V of t plus 20. So we're just going to take this exact graph and move it up. Here, we'll make this one red for the new one. So we'll move it up 20. So if this is at 0, you go up to 20. And if this is at, say, 25 or so, it's going to go up to 245. Same thing here. And then this is going to go up to 20. So basically everything's just going to get shifted up 20 units. So it'll be the same basic shape, or the exact same shape. Maybe I should use lines, make it look a little nicer. Let's try that again. Let me do it red. There. 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 So it's just, again, it's just being shifted by 20 units up. So it's the exact same shape, everything just lifted up 20 units. How to, given a tabular function, create a new row to represent a vertical shift. So we're going to first identify the output row or column, determine the magnitude of the shift, add the shift value to each output cell, add a positive value for up or a negative value for down. Okay, so if we wanted to shift this graph in example 2 vertically, we're going to basically take all the output values of the original function, f of x, right? So remember, this is the output value for the given x. And we're going to, looks like we're going to shift it down 3 units. So we're going to subtract 3 units from all the y coordinates. So for our next, so x is going to stay the same, and then we're just going to subtract 3 from each of these y values. So 1 minus 3 would be -2. 3 minus 3 would be 0. 7 minus 3 would be 4. And 11 minus 3 would be 8. So for our g function, x would be 2, y would be -2. X would be 4, y would be 0, x would be 6, y would be 4, x would be 8, y would be 8. All right, so that's basically going to have the exact same shape as the original function, but just shifted down 3 units. Identifying horizontal shifts. Horizontal shift. Given a function f, a new function g of x is equal to f of x minus h. Notice the minus h is in the parentheses with the x. So you're going to subtract the number from x first and then get the output value. So h is a constant. It's a horizontal shift of the function f. Now if h is positive, the graph will shift right. If h is negative, the graph will shift left. But notice we have a minus sign here. So if it's x minus 3, h is positive 3 because you got to write it as a subtraction. So that's kind of confusing. So I just say, okay, it's going to be the opposite of this. So if it's minus 3, you go plus 3. If it's plus 3, you go minus 3, right? And then, so basically you do the opposite. So let me show you on Desmos. Okay, so we're still using the same basic parabola from our toolkit function, but you can use any function for these transformations, right? So you know all the basic functions, the toolkit ones, and then you learn these transformations, and then you can basically graph any variant of that basic function. All right, so here, now notice, now this is a little confusing. So if h is 1, then in the parentheses would be x minus 1, and see it's going to go to the right one. So this would be, for instance, if I wrote, here, let's write it actually like that. So let me get rid of this slider and just show you. So if x is minus 1, you actually go plus 1. If it's minus 2, you go plus 2. So you see how that shifted 2 units to the right? So it's going to be the opposite of the sign because of the way it's given in the formula. So if I do minus a minus 2, well, that's the same thing as plus 2. So see, and then that will get shifted to negative 2, right? So if you look at the vertex, it's going to get shifted to negative 2. Okay, and every point, this point would get shifted, this point right here, 2, 4 would get shifted 2 units to the right. So it'll be 0, 4. It's not cooperating with me there. There you go. Okay, so again, it's going to be whatever the opposite. So if I have minus 3, that's going to shift the parabola to 3 units to the right. Okay, so that's the horizontal shift. Example 3, adding a constant to an input. So returning to our building airflow example from figure 3, suppose that in autumn, the facilities manager decides that the original vending plan starts too late and wants to begin the entire vending program 2 hours earlier. Sketch the graph of the new function. So if we want to start it 2 hours earlier, we're going to shift this 2 units to the left. So the new one would be, so that this 0, 0 will get shifted to here, minus 2, 0. And then this 8, 0 gets shifted back 2 units, so it'll be 6, 0. And then let's see, this one is about 10, whatever the 220, 220. So subtract 2 hours. So everything's getting shifted to the left 2 units. So this is probably going to go right about there. This one 2 units right about there. And there. And then we're going to connect those dots. So still in red. Okay, so that's our new graph. It's the exact same shape as the blue one, just shifted 2 units, or 2 hours, which is 2 units, to the left. Oh, and then if I wanted it, if I called, if we called, so remember the blue one was y is equal to f of x. So the red one would be g of x is, and we're moving it 2 units, so it'd be x minus a minus 2, which becomes plus 2. Well, it's not x, it's t. And I think we used v for the, yeah, so the y value is v, so this should be v. And then t minus a minus 2, so plus 2, and then that shifts the graph 2 units to the left. How to, given a tabular function, create a new row to represent a horizontal shift. Identify the input row or column, determine the magnitude of the shift, add the shift to the value in each input cell. So remember, because of the way this works is we're going to do the opposite. So this would be minus 3, so the actual shift is plus 3. So we're going to add 3 units to each of the x values to get our new x value. Okay, I'm not 100% sure I like the way the book presents this. This is the way I think of it. Okay, so again, remember, you're going to do the opposite of this. So we're going to add 3 to all the x values to get our new x value for our new xy chart. Okay, so we're going to do 2. We're going to add 3 to each of these, and we're going to leave the y value alone. Okay, so it'll be 2 plus 3 would be 5. And see, if you were to plug 5, so remember, g of x is f of x minus 3. So if I put in g of 5, you're going to do 5 minus 3. You do this first, which gets you 2. And then the f of 2 is going to get you 1. So see, so if we build the new function, you're going to do the opposite of minus 3. You're going to add 3. So this would be 5, and the y value stays the same. So 4 plus 3 is 7, and the y value stays the same. 6 plus 3 is 9. Y value stays the same. 8 plus 3 is 11, and then the y value stays the same. Okay, so that's kind of the way I do it. It's a little bit presented a little bit differently in the book. You can read that and decide which way makes more sense to you. But this is the way I'm kind of refer to it. Example 5, identifying a horizontal shift of a toolkit function. Figure 8 represents a transformation of toolkit function f of x equals x squared. Relate this new function g of x to f of x and then find a formula for g of x. So if you recall, our basic toolkit function f of x is equal to x squared is a parabola, and then it starts at 0, 0, 0 squared, 0, 1, 1, 2, 4, and then negative 1, 1, negative 2, 4. So our parabola will be here, and what we're doing is we're shifting, the vertex is going that way, so it's going right 2 units. This point gets shifted 2 units that way. This one gets shifted 2 units that way. So remember, a horizontal shift is going to be, so g of x is going to be f of x. Let's go back to black. F of x, and we're shifting it 2 units to the right, so this is going to be minus 2, because remember it does the opposite. So plus 2, we want minus 2 in here. Okay, so that would be, so then we're going to take this x minus 2 and plug it into the f of x function. So that would be x minus 2 squared. And you can leave it like this. You don't have to multiply that out. I mean, if you wanted to, you could. You can write it like this, or you can go ahead and multiply it out and get x squared minus 4x plus 4. I would prefer it this way because then I can see the transformation. I can graph it real easily. Let me show you both of those plugged into Desmos so you can see that it's the same. Okay, so we had the x squared, well, what did we say? Minus 2, right? That's the one we want. So if I typed in, let's turn this off, typed in parenthesis x minus 2 squared, you can see it's the same graph. So that's the original one. Then if I shift it 2 units, you can see how you can't even see the difference there, right? I mean, you can see the color change. Okay, so, and then if I typed in x squared, just copy and paste it, x squared plus, no, what was it? It was minus 4x plus 4. You can see it's the same graph. Okay, so again, I would personally prefer to leave it like this way, because then I can see the transformation. It's just my basic square function shifted 2 units to the right. Example 6, interpreting horizontal versus vertical shifts. The function g of m gives the number of gallons of gas required to drive m miles. Interpret g of m plus 10 with the plus 10 outside. So that's the way I think of it. It's outside. Remember, g of m is your output value, and you're adding 10 to the output value. So G of m is the number of gallons of gas required to drive m miles. So this is going to be the number, we're going to add 10 to the output of gallons. So this is going to be 10 gallons extra than whatever is required. And then G of m plus 10, the plus 10's on the inside, it's acting on the input value. So this is going to basically say how many gallons of gas do we need to drive an extra 10 miles, right? So that's because we're acting on the input value. So that'd be an extra 10 miles. Combining vertical and horizontal shifts. Given a function and both a vertical and horizontal shift, sketch the graph. So basically you're going to first identify the vertical and horizontal shifts from the formula. The vertical shift results from a constant added to the output. That's outside the function. Move the graph up for a positive constant, down for a negative constant. Then you're going to determine the horizontal shift results from a constant added to the input. move the graph left for a positive constant and right for a negative constant. So see here they kind of changed their tune here. So remember, you're going to do the opposite. That's kind of the way I've been talking about it. And then apply the shifts to the graph in either order, right? So you can do it in either order. Graphing combined vertical and horizontal shifts. So given f of x equal to absolute value of x, so again, that's one of our toolkit functions. So if you remember absolute value, so x, y, we're going to do 0, absolute value 0, 0, absolute value 1 is 1, absolute value 2 is 2, and then if we do the negative side, absolute value -1 is +1, absolute value -2 is +2, and you get a V. So I can keep going 3, 3 if I want to do more than on my table there. And then I'm going to get a V. Okay, so that's my absolute value function. Now the +1, so this is going to shift it left 1 unit. And then the -3, is going to shift it down. So remember, if it's inside acting on the input value, it does the opposite. So this one would be -1, and if it's outside, that's going up and down, and it does it the same way. So inside, it's acting on x, x is side to side. So that's the horizontal. So this would be left 1. This is outside, it's acting on the y, that's the way I think of it. So it's doing up-down shifts. So, and it does direct. So if it's -3, you go down 3. If it's +3, you go up 3. So we're going to take each of these points, and you can do it either order. You're going to shift it 1 unit left and down 3. Oh, I didn't make my graph big enough. Darn it. Okay, let me try this again. Okay, so I changed the graph. So I'll do red for the new graph. So the 0, 0 is going to get shifted left 1 unit, down 3. So now the way that I actually do this is then I go back to my original graph. So I'm not going to take each point and shift it left 1 unit, down 3. I mean, you could certainly can do that. Then this one, left 1, down 3. What I do is I call, like this one, it's a absolute value, and you have the vertex, and I get shifted, and I call this the pretend origin, like this. So this dotted x is going to be my pretend origin. I'm going to pretend that's x and y, and from here I'm just going to plot this counting from my pretend origin. That's the way I do it. Now my pretend origin, if it's going left 1, down 3, this is my pretend origin. Okay, so counting from here, I'm going to do 0, 0, 1, 1, go back to the pretend origin, 2, 2, back to pretend origin, 1, 2, 3, 1, 2, 3, and then I'm going to do my negative side, -1, 1, -2, 2, and let's do this one in red. So that is my transform graph from the original graph, and I shifted it left 1 unit and down 3 units. Example 8, identifying combined vertical and horizontal shifts. Write a formula for the graph shown in figure 11, which is a transformation of the toolkit square root function. So if you recall, toolkit square root function, if you do square root of 0, 0, square root of 1 is 1, the next nice one, square root of 2 is 1 point something, 1.4. The next nice one's going to be 4, square root of 4 is 2, and then the next one would be 9, 3, and it has this shape like here, but it starts at 0, 0. So this is going to start here, and we're shifting 1 unit right and 2 units up. So if you remember to do a horizontal shift, if we want to do +1, we got to write -1. So for our transform graph, we're going to take our original graph. Oh, you know what? They're calling it h of x. So h of x is going to be our toolkit f of x, and we're shifting it right 1, so this would be -1, and then up 2, so then you do the +2 outside. And our toolkit function's the square root of x, so we're going to put the x minus 1 on the inside for the radicand, for the x, and then the +2 outside. Right, so that will be our answer for the, if we want the formula for that square root function. Learning objective 2, graph functions using reflections about the x-axis and the y-axis. Graphing functions using reflections about the axis. Okay, so here's the original function, this blue one, right, the solid one. This curve looks like an exponential function, which we'll learn about later. If I were to reflect across the y-axis, so you take this point right here where the arrow's starting, and you reflect it across the y-axis, that's what we call a horizontal reflection. Okay, so you're flipping it that way. And then if I flip it over the x-axis, that's a vertical reflection. Okay, so if you can think of the axis as, you can think of it as a mirror. If you look in the mirror, this point will look like it's over there. This point will look like it's over there, right? So flip it. Another way to think of it is if you were to, if this is on a piece of paper, if you flip the paper, if you hold your finger on where the Y is and down here on that arrowhead and flip the paper over that way, this way, right? It's hard to see. It would flip around and you get that reflection, is what we call a reflection. And then if I flip it over the x-axis, it would flip it upside down. So for reflections, given a function f of x, a new function g of x is equal to negative f of x is a vertical reflection of the function f of x, sometimes called a reflection about or over or through the x-axis. Right, so you can use any of those terminologies. Reflection about the x-axis, reflection over the x-axis, reflection through the x-axis. Right, so those are all common. Given a function f of x, a new function g of x is equal to f, and notice where the -1 is in here, or the negative sign. Negative x is inside the parentheses. So that's acting on the x, and remember f of x means y. So see, the negatives acting on the y. Y is up and down, x is side to side. So the top one's a vertical reflection, the bottom one's a horizontal reflection. That's kind of how I keep it straight in my head. Okay, so that's called a reflection about the y-axis on the bottom one. And just to kind of reiterate here, so if I wanted to reflect it about the x-axis, if I take this point and I reflect it through the x-axis, basically it's going to be the same distance on the other side. So you can see the y value, that if I called that f of x, it'd be negative f of x, or negative y, or the opposite of y. If I want to reflect it through the y-axis, it'll pop up on this side, and again it has to be that same distance. So if this is, say, 3, 4, then this would be negative 3, 4. So you're just going to switch the sign of the x coordinate, and the y coordinate stays the same. Okay, so this is a reflection through the y-axis. This one's a reflection through the x-axis. How to, given a function, reflect the graph both vertically and horizontally. Multiply all the outputs by -1 for a vertical reflection. So that's basically what I was drawing. You're going to take every y coordinate, times it by -1, or just change the sign of the y coordinate. Okay, and that would be the reflection of the original graph through the x-axis. And then if you want to do it through the horizontally, that's through the y-axis. Multiply all the inputs, so you're going to do the inputs. You're going to change the x value. So if you multiply something by -1, it changes the sign of it. So you're going to take all the x values and change their sign. And if I take the x value, change its sign, it's going to be a reflection through the y-axis. Okay? Example 9, reflecting a graph horizontally and vertically. So reflect the graph of s of t, which equals square root of t, vertically and horizontally. So we're going to do both. So if you remember our basic toolkit function, if I have y is equal to square root of t, I'm going to write t since it's here, t and y, or x and y if you want. Square root of 0 is 0, square root of 1 is 1, square root of 2 is 1.4, square root of 3 is 1.7, square root of 4 is 2. And again, the next nice one would be 9. So this is our original function, 0, 0, 1, 1, 4, 2, 9. So remember, you start 0, 0. So 9 is the x coordinate, 3 is the y coordinate. So 9, 3. And then you get that square root function shape. Oops. It's kind of hard with this tablet I'm using. But anyway, kind of bad, but close enough. All right, so we're going to reflect it. So remember, our how-to is, if I want to reflect it, let's see, which one is this one? Reflect it, multiply all the outputs by -1 for a vertical reflection. So if I want to reflect it vertically, I'm going to take all the outputs and multiply them by -1. So if I multiply all these by -1, it'll be 0, 0, 1, -1, 4, -2, 9, -3. Let's do this one in blue, this blue. So 0, 0, 1, negative. So I'm looking at this one, my reflect across, or about, or through x-axis. Right, so that's a vertical reflection. So 1, -1, 4, -2, 9, -3, and then it's the same graph, but see, all these points got reflected down, so it's the same graph. Again, that's pretty bad, but should be smooth, right? That's even worse. Okay, so that's the vertical reflection. And then that was A. Now we want to do horizontally. So horizontally, let's do this one in red. horizontally, we're going to, let's start from our original one. And then we have to multiply all the inputs by -1. So we get -1 times 0 is 0, -1 times 1 is -1, and the y coordinates are going to stay the same. So again, and then if you want to do it visually, if I reflect it through the x-axis, if we're here at 1, we go 1 in the opposite direction. This is at 4, we're going to go to -4. This is at 9, we're going to -9. Right? Or you can plot these points. 0, 0, -1, 1, -4, 2, -9, 3, and then you get I don't know why I can't do it on this tablet. I can do it really good on a whiteboard, but I haven't been using this tablet enough. Anyway, I'm going to give up. I'll have to get better. Alright, that's a little bit better. Actually, a lot better than that last one I had. Okay, so you can see the red ones are a reflection across the y-axis, or a horizontal reflection, and the blue one is a vertical reflection, or reflected through the x-axis, right? You can think of it either way. Okay, reflecting a tabular function horizontally and vertically, a function f of x is given in table 6. That's this one here. We're going to do g of x is equal to negative f of x. So again, we're going to do x g of x, which is equal to negative f of x. Okay, so negative f of x is, remember, f of x is the y value, and you're timesing the y value by -1. So for this one, we're going to times the y value by -1. We're going to leave the x values alone. So it'll be 2, -1. That'll be 4, -3. 6, -7. 8, -11. Okay. Then we're going to do x. Okay, so this is A. Now we're going to do B. X h of x. Now h of x is f of negative x. So we do the negative times 1. Negative, remember, the opposite of x means -1 times x. We're going to do the -1 times the input values. So let's erase all these babies. Hopefully that is, oh, I knew it. Okay, let me try that again. There we go. Okay, so now we're going to multiply just the x coordinate, the input values, by -1, and we're going to leave the y values alone. So we get -2, 1, -4, 3, -6, 7, and -8, 11. Example 11, applying a learning model equation. A common model for learning has an equation similar to k of t is equal to -2. So this really should be read as the opposite of 2 to the -t plus 1, where k is the percentage of mastery that can be achieved after t practice sessions. This is a transformation of f of t is equal to 2 to the t, which is an exponential function that's shown down here, figure 15, sketch graph of the transform k of t, right? So this one is a challenging one. You have three transformations. You have a reflection. Let's see, this is a reflection of across the Y. So this way, right? That's a horizontal reflection. No, across the Y would be this way. And then a vertical. And then the minus t is up within the function. So that's the horizontal one. So you got a reflection across the y-axis. No, this is the y-axis. This is a horizontal reflection. That's across, horizontals across the y-axis. Okay, you're going to change, y-axis is, you're going to change the input value, change input. Oops, put. Okay, and then this one is your vertical reflection, reflex. So that one vertical, it's going to go flip it upside down. That's through the x-axis. It's kind of confusing because when you say we do it through, it's a vertical translation through the x-axis, but see, you're changing the y value. Okay, so the x value stays the same, but the y value switches. So we're going to do those two, and then finally we're going to do a vertical shift of +1. So technically you should do it in this, I think you could probably interchange these. It doesn't matter which order you do those, but you got to do the +1 after you do the reflections. So you got to do the reflections first and then the +1. Okay, so basically, let me see if I can get a new graph here to graph it. I'll just do it on this one. Okay, so we're going to flip it around. So let's see if we're here at like 2, and it looks like, well, let's see. This one's going to stay in the same spot. Let's do the horizontal reflection first, this one. So this is at 2, so it's going to move to -2 right there. And then this one's at 1, so it's going to move to -1. This one's at -1, so it goes to 1, 2, -3. So that's going to be our curve from there. Okay, then we're going to take that and flip it over the t-axis or x-axis. So we're here at about 3.5 or so. So we're going to go down to -3.5. Now let's change colors here. Let's change it to blue. Or purple. It's a little different shade than that one, so we're good. Down 2. This one's at 1, so it goes to -1. This is about half. This is about 1/4, 1/8, roughly. Okay. And then we're going to shift it up 1 unit. So now we're going to move all these. So let me erase the red. And then I'm going to shift it up 1 unit. So let me do it with this green color. All right, so we're going to shift it up. So this is at -1, so it's going to go to 0. This is at -1/2, so it's going to go to +1/2. It's about 1/4, so 3/4. It's at -1/4. So anyway, and you see how this is what we call an asymptote. So it's approaching that. Again, we're just going to go up 1. So our graph, our final graph is going to be, oops, let me try that again. And again, it shouldn't hit the one there. It's going to be just the shade below it. Okay, so that will be our final graph there. Okay, on to the next learning objective. Determine whether a function is even, odd, or neither from its graph. Determining even and odd functions. A function is called an even function if for every input x, f of x is equal to f of negative x. The graph of an even function is symmetric about the y-axis. So what that means is, if you think about, it's kind of like the reflection, but the before and after image looks the same when you reflect it through the y-axis. So for instance, if you have a parabola and you reflect it through the y-axis, this point goes to there and that point, right? Both of these give you the same. So when you switch every point on this graph and you flip it over the y-axis, it's going to look like the original function. So that's saying that the y value for x and negative x are going to be the same. So if this was x, f of x, and if I change the y value, if I change the x value, negative x, and then f of negative x, that's going to be the same y value, right? These have the same y value. So f of x and f of negative x are the same y value, right? Those are going to be the same. Okay? A function is called an odd function if for every input x, f of x is equal to the opposite of f of negative x. Actually, typically when you see this in books, other books, it's the opposite of, this is the way I like to see it. F of negative x is the opposite of f of x. That's typically the way we do it. Anyway, this probably means the same thing. The graph of an odd function is symmetric about the origin. We haven't talked about symmetric about the origin. So symmetric about the origin is if you have an xy and you want to be symmetric through the origin, you got to change both coordinates. So be negative x, negative y. Okay? And then that's kind of where this comes from. If you switch the x coordinate, you got to switch the y coordinate. Okay, so you switch both of them to be symmetric to the origin. Okay, example 12. Determine whether the function is even, odd, or neither. Is the function f of x equal to x cubed plus 2x even, odd, or neither? So the tests, you're going to run both tests from what we learned in the definition here, right? You're going to plug in negative x and see if when you plug in negative x, does it give you f of x or does it give you, this is why I like the way I defined it. If you plug in negative x, do you get negative f of x? This is the way they define it. All right, so let's try it. So for even, f of negative x is equal to negative x cubed plus 2 times negative x. And then if you raise this to an odd power, right? So negative x is the same thing as negative 1 times x. So if I raise that to an odd power, using my power rules, it's going to be negative 1 to the third, x to the third, and negative 1 to the third is negative x to the third. So this becomes negative x to the third, and then 2 times negative x is negative x, which if you, now, if we use their definition, right, does this equal, is f of x is x cubed minus or plus 2x. So are these equal to each other? Is negative x cubed Are these equal to each other? Sorry. Got lost in my thought for a second there. Okay, so are these equal to each other? And the answer is no, they're not, right? So it's not even. Okay, now we're going to try the odd one. And then if odd fails, so what we're trying to do for odd is we're seeing is f of x, if we use their definition, negative f of negative x. Well, f of negative x is what I have written here, right? So I'm going to take the opposite of that. I'm going to write negative as negative 1 times negative x cubed minus x. So I distribute the minus sign and I get x cubed plus x. And then you can see f of x is equal to, so yes. Did I copy this wrong? This should have been 2x. See, now they're equal. I copied this wrong, darn it. So they're still not equal here. So it's not even, but see, they're equal here. So yes, it's even. I mean, yes, it's odd. So that's an odd function. Now, what does that mean? So if I were to graph it, that tells me that it's symmetric about the origin, which means I can cut my work in half, because if I know, for instance, 3, 7 is in the graph, then I know the symmetric point where you change both signs. So if it takes me some work to figure out this one, I essentially get this one for free. So that cuts your work in half. And the way it looks visually, here, let me graph this on Desmos and show you. Oh, they had the picture in the book. So here's the graph of it. Now look, if I were to put my finger, if this is on a piece of paper and I put my finger right at the origin, this is what I neglect. If I spin it 180 degrees, and if you didn't know that I spun it 180 degrees, it would look identical to where it started. Okay, that's symmetric about the origin, right? So that shape is the same whether I look at it that way or spin it 180 degrees. And again, if I did the math to figure out 1, 3 is on the graph, you know, by plugging in 1 for x, and I do 1 cubed plus, let's see, what is the equation? So if I did 1 cubed plus 2 times 1, well, that's 3. So if 1, 3 is in the graph, I just made this in thin air. So if I had 1, 3 in the graph, that automatically tells me that negative 1, negative 3 is in the graph, or on the graph. Okay, so I automatically get that one, I say for free, right? I don't have, so I do the work to figure this one out. I get that one for free if I know symmetry. Okay, next learning objective, graph functions using compressions and stretches. All right, vertical stretches and compressions. So again, the solid blue ones are original function. And if we want to vertically stretch it by a factor of 2, basically you're going to take every y coordinate. So let's say this was at 3. 3 times 2 would be 6. And it gets stretched, vertically stretched by a factor of 2. And then this point is, let's say it's at 2, and then 2 times 2 would be 4, right? And you would stretch it by a factor of 2. And then compression is the other way, is you're going to, some books say shrink. I like compress because I think of if I push it down, right? So if I chop it in half, it compresses it. Okay, so same thing. So this one's cutting it in half. So that's compression. This one's taking it, multiplying it by a factor of 2. So that's vertically stretches it. Okay, so you got a vertical stretch if that's bigger than 1, and if it's between 0 and 1, or it's the absolute values between 0 and 1, that's a compression. vertical stretches and compressions. Given a function f of x, a new function g of x equals a times f of x, where a is a constant, is a vertical stretch or a vertical compression of the function f of x. So the way you know if it's stretch or compression, what I was mentioning on the graph, if a is bigger than 1, it's a stretch. If it's between 0 and 1, it's a compression. Now if it's negative, right, if a is less than 0, that means if it's negative, then the negative part's the reflection across the x-axis, the vertical reflection. And if the absolute value is between 0 and 1, it'll be compressed. So it'll be compressed and flipped over. And if the absolute value is greater than 1, so if it's like negative 1.7, that would be a stretch of 1.7, and the negative does the vertical reflection. So it's a combination of a stretch or compression with the reflection. Okay? And then the technique is here. Basically, we're just going to figure out what's A and multiply all the Y values, the output values, by A. Okay? And then if you do that, you don't necessarily have to worry about the words here. I mean, it'll take care of itself. But if A is bigger than 1, it'll be a stretch. If it's between 0 and 1, it'll be a compression. If it's negative, it's a vertical reflection combined with either a stretch or compression, depending on what the absolute value is. Example 13, graphing a vertical stretch. A function p of t models the population of fruit flies. The graph is shown in figure 20. A scientist is comparing this population to another population, Q, whose growth follows the same pattern but is twice as large. Sketch the graph. So we're going to scale this by a factor of 2, or stretch it by a factor of 2. So Q of t is equal to 2 times P of t. So we're going to, so our scaling factor is 2. 2 is bigger than 1, so it's going to be a stretch, a vertical stretch, right? So we're going to multiply all the Y values by 2. And we're going to leave the X, or the T in this case. Leave it alone. So at this point, 0, 1, right? So if we have T and P of t, we got 0, 1. We're going to multiply the 1 by 2, and that's going to give us T Q of t. So that'll be 0, 2. So let me change this to red. So 0, 2. And then you see how this is at like 1.2, so that'll be like 2.4. I just go to like these like the kind of endpoints of segments where they change. So here this is 3, so I have 3, 3, and then times it by 2, so that'll be 3, 6. So 3, 6, and then I'm going to kind of match that curve, but with the vertical stretch. Or you can, you can pick out that's like 1.9, so 3.8 if you want to do that kind of thing. And then this one is 6, 2, so times the y coordinate by 2, so it'll be 6, 4. And then 7, 0 stays there. And then this is a straight line, so we just connect it with a straight line. And then that line segment is a straight line segment. And there you go. So that is the same basic shape, but with but it's been stretched, vertically stretched. So it distorts the shape a little bit, right? But it still has the same basic shape, just distorted by stretching it vertically by a factor of 2. Okay, example 14, find a vertical compression of a tabular function. So a function f is given in table 10, which is right here. Create a table for the function g of x equals 1/2 of f of x. Okay, so if we're going to do x, g of x, remember g of x is 1/2 of f of x. So we're going to take, remember this is the y coordinate or the output value for each given x. So we're going to multiply all these by 1/2 to create our new function. So the x, we're going to leave it alone. 1 times 1/2 is 1/2. X, leave it alone. 3 times 1/2 is 3/2 or 1.5. 6, leave it alone. 7 times 1/2 would be 3.5 or 7/2. We'll just leave it that way. And then 8, leave it alone. 11/2 or 5.5 or 5 1/2. Erase. I'll leave it so you can see what I did. Recognizing a vertical stretch. The graph in figure 22 is a transformation of the toolkit function f of x equals x cubed, right, our cube function. Relate this new function g of x to f of x and then find a formula for g of x. So if you recall, our toolkit function for y is equal to x cubed is x, or you can call this f of x. Remember, y is f of x. Is going to be 0, 0, 1, 1, 2 cubes, 8. And then if we do -1 cubed, it's -1. -2 cubed is -8. So 0, 0. Here, let me do it in red. 0, 0, 1, 1, 2, 8. -1, 1, 2, -8. So it's way down here somewhere, and then it does this. That goes up to 8. So let's see here. This factor is, where does it hit 1? So we're doing a factor by, let's see, this one, 2 would go to 8. So we're actually compressing it, right? And then this goes down to, so if this was at 8 and it goes down to 2, we're timesing it by 1/4. We're compressing it. So if we do g of x is 1/4 times f of x. Okay, so if you multiply these by 1/4, you would get the graph, the blue graph that's here. Okay, so it's getting compressed. So let's see here. So then g of x is equal to 1/4 f of x, but f of x is x cubed. So that's my answer, 1/4 x cubed. Okay, so horizontal stretches and compressions, we can do the same thing. I don't know why they started this over here. It should start here. So if blue's our original function, and if we do it by 0.5, it's actually, remember, the thing you got to remember, if you're acting inside on the x before you do the function, it does the opposite effect. So if you're multiplying by 0.5, multiplying by 0.5, same thing as dividing by 2 or timesing by 1/2. So then you do the opposite operation of multiplying is dividing, or if you divide by 2, you're going to multiply by 2. That's, so you do the opposite. Okay, so if this is 1/2, you're going to stretch it by a factor of 2. If this is 2x inside, you're going to compress it by a factor of 1/2, right? You're going to divide it by 2. So if you're multiplying by 2 in here, you're going to take the x coordinate and divide by 2. Given a function f of x, a new function g of x equals f of b times x inside the parentheses here, where b is a constant, is a horizontal stretch or compression of the function f of x. If b is greater than 1, then the graph will be compressed by 1 divided by b. So if you're multiplying by 5, you're actually going to do 1/5, or divide by 5. Okay, if b is between 0 and 1, then it's going to be stretched by 1 over b, which is the way you can read this one would be the reciprocal. So if b is 1/2, then 1 over 1/2 is multiplied by 2. If b is less than 0, it's a combination of a stretch or compression with the reflection, horizontal reflection. Okay, so given a description of a function, sketch a horizontal compression or stretch, write the formula, represent the function, set g of x equals to f of b of x, where b is greater than 1 for a compression, or 0 is less than b is less than 1, so b is between 0 and 1 for a stretch. Example 16, graphing a horizontal compression. Suppose a scientist is comparing a population of fruit flies to a population that progresses through its lifespan twice as fast as the original population. In other words, this new population R will progress in 1 hour the same amount as the original population does in 2 hours, and in 2 hours it will progress as much as the original population does in 4 hours. Sketch the graph of this population. Okay, so here's our graph for a population of fruit flies, and remember our R of t is going to be twice as fast, so that's going to be p of 2t. So R of 1 is going to be equal to R of 2. Okay, so what we're doing is we're going to take each coordinate, so we have 0, I'm going to just write xy, 0, 1, and we're multiplying the, I guess I should have wrote t. We're taking the t value and multiplying it by 1/2, right? We're dividing by 2. So that's going to get us 0, 1. And then if I do t and R of t. And then if I do, this one is 3, 3, and I'm going to multiply that by 1/2. So that'd be 3/2, or 1.53. So it goes to here. Let me do this in red again. So 0, 0 stays, 0, 1 stays put. 3, 3 gets pushed, compressed horizontally. And then this one, 6, 3 times this by 1/2. No, that's 6, 2, sorry. So that'll be 3, 2. And then 7, 0 times 1/2 would be 7/2, 0. So 7/2 is the same as 3.5. We have this curve, and then straight line segments, that, and then that one. So that's our graph. So the red one would be our new graph. Okay, so again, finding a horizontal stretch for a tabular function. A function f of x is given in the table. Create a table for the function g of x, which equals f of 1/2 of x. And remember, if you want to use terminology that I do, I'm saying we're doing 1/2 is acting on the x. It's inside the function, and it does the opposite operation. So if it's multiplied by 1/2, you're going to divide by 1/2. Dividing by 1/2 is the same thing as multiplying by 2. Okay, so we're going to multiply the x coordinates by 2, and we're going to leave the y coordinates alone. So 2 times 2 would be 4. The y coordinate stays 1. 4 times 2 is 8. 3. Oops, I multiplied. That one stays the same. And then 6 times 2 is 12. 7 stays the same. 8 times 2 is 16. The y coordinate stays the same. Okay, so this 1/2 is acting on the x. You do this first, and it has the opposite effect. So if it's divide by 2 or times by 1/2, that's the same thing as we do the opposite. So from times we do divide. Dividing by 1/2, same thing as timesing by 2 or multiplying by 2. Example 18, recognizing horizontal compression on a graph. Relate the function g of x, so that's the red one, to f of x, which is the blue one. So again, what I look for is I look at the usually endpoints or vertices, or like this point right here. I could see that the transform point is right there. So that looks like it's doing some kind of transformation, compression horizontally. See, that point's going over to there. This point's going over to there. This point's going over to that point. So on. So what's that factor? So, look for nice ones. So this point here is, let me erase all that stuff I just did. And let's just focus on that first one. So 6, 4 is being transformed to 2, 4. And we're just pushing it sideways. It's not a shift because the shape is distorted. So that's how you can tell that it's, okay, this is a compression. Right? If it's shift, if this is being shifted 1, 2, 3, 4, all the points get shifted 4, and the shape doesn't get distorted. So you can say, okay, that looks like a compression. So if I look at this one, I'm taking 6 and I'm multiplying 6 by what to get to 2. So I'm multiplying it by 1/3. So 6 times 1/3 is 2. Right, to get my transformation here. So I'm going to say g of x is f of, remember you do the opposite, so it'll be times 3x. Okay, and then that's your answer. And for our last learning objective for today is combine transformations. Performing a sequence of transformations, meaning we're going to combine transformations. So combining transformations. When combining vertical transformations written in the form of a f of x plus k, first vertically stretch by a, then vertically shift by k. So you got to do the stretch first, and then the stretch or compression, and then the vertical shift, right? So you got to do, I think of it, it's basically like order operations, right? So if you think about, okay, if I put a number in for x, do the function, you get a y value, then you're going to multiply it by a, and then you're going to add the k, right? So you got to do the a first, then the k. So if you do it with the horizontal transformations, put the x in first, you're going to multiply by b first, and then subtract h. So you got to do the horizontal shifting, right? The stretch or compression. Oh, they're doing it backwards. Oh, yeah. the way it's written, right? You're going to do this first, and because remember we're doing it, it has the opposite effect. So you're going to do the plus h and then divide by b, right? So plus h and then divide by b. And then when you're combining it written in this form where the b's factored out, first you're going to do the 1 over b, right? You're going to divide by b, and then you're going to add h. So again, if you think order operations, but if you're inside acting on the x, you actually go backwards, right? And you do the opposite. So you're going to divide by b, and you're going to add h. Horizontal vertical transformation are independent, so it doesn't matter where you do horizontal vertical transformations are performed first. I tend to like to do it like what I was saying, the order operations kind of idea is the way I do it, but again, it doesn't matter for horizontal. So those, other than the restrictions listed above, you can do vertical and horizontal separate. They're independent. Finding a triple transformation of a tabular function. Given table 15, create a table of values for the function g of x is equal to 2 times f of 3x plus 1. So I'm going to do, let's see here, the 3x, that means we're going to divide by 3 or times by 1/3, whichever way you want to think of that. I'm going to divide by 3 since these are all multiples of 3. So times by 1/3 or divide by 3. And then I'm going to take the y value times 2 and then add 1. So times 2 and then add 1. Times 2, then add 1. Times 2, then add 1. Times 2, then add 1. So this would be my new x, g of x. So 6 divided by 3 is 2. And then I get 20 plus 1, 21. 12 divided by 3 is 4. 28 plus 1 is 29. 18 divided by 3 is 6. 30 plus 1, 31. 24 divided by 3 is 8. 34 plus 1 is 35. And that is my transformed function. Okay, so use the graph of f of x in figure 27 to sketch the graph of k of x is equal to f of 1/2 x plus 1 minus 3. So there's two ways we can do this. We can factor out the 1/2 and do, let's see, we can view it this way, right? Or we can just leave it the way it is and we can shift it horizontally by h, but remember it's going to be the opposite. So, and then you're going to stretch it by a factor of 1 by b, right? 1b. So, I think that should have been 1 over b, but anyway. Okay, so 1/2. So that means we're going to shift it 1 unit, minus 1. So the 2, 0. This is my x, f of x. So I'm going to subtract 1 from the 2, which gets me to 1. And then I'm going to multiply it by 2, which gets me 2. And then I'm going to shift it vertically by 3 units. So 0 minus 3 would be minus 3. So this point's going to go to 2 minus 3. Okay, and then this point is 0, 2. And let's see, we're going to subtract 1 first. Right? Subtract 1, so that's going to get us to -1. And then we're going to do the opposite of multiplying by 1/2, which is dividing by 1/2, which is multiplying by 2. I guess I should have wrote the 2. It doesn't matter what side you write it on. It's multiplication. So that gets me -2, and then I subtract 3 from the y coordinate. So 2 minus 3 would be -1. So this point goes to -2, -1 up here. And then this point is -2, 0. So I'm going to subtract 1. So -2 minus 1 is -3. Then I'm going to times by 2, which equals -6. And then I'm going to subtract 3 from the y coordinate. And that gets me a -3. And it's going to be the same semicircle, but it was horizontally stretched by a factor of 2, so it's going to be more of an oval shape now. So -6, 3. Okay, so it's going to be an oval shape. Again, there's my horrible drawing on this tablet. I'm not very good with the tablet. I'm going to blame it on the tablet, but I'm pretty good on the whiteboard, but I'm not great. But that's pretty bad. All right, but hopefully you got the idea. Okay, and that brings us to the end of that lesson. That was a really long one. I know in our other book that we use, they split this section into 2 sections because of how long it is. But anyway, you're done. Make sure you do a lot of practice in the exercise set. Practice, practice, practice. I'm going to start saying that every time. All right, have a good day, and I'll see you next time.